Hi, everyone. My name is Marty Fulton, and I'm with the Storage Networking Industry Association. I'm taking over as your moderator for the afternoon sessions today. I'm very pleased to switch to a new topic for SNIA on security, but also melding it a little bit with computational storage, and introduce our speaker, David McIntyre, the Director of Product Planning and Business Enablement with Samsung Corporation. David focuses on computational storage acceleration solutions development and strategic business enablement for cloud-to-edge applications. His framework of research includes AI inference, video analytics, held senior positions at a number of companies, including some Silicon Valley startups. And he's also consulted for institutional investors, including Fidelity, Goldman Sachs, and UPS. He's a frequent presenter and speaker at a number of conferences, including Flash Memory Summit and SNIA Storage Developer Conferences. So let me introduce David. Take it away.
Welcome, everybody. Let me switch to my screen here, and we'll get started. Okay. There. All right, so as Marty said, I'm going to focus on computational storage and some of the new security challenges and solutions around those challenges for the hybrid cloud space, which is, of course, a very hot and growing space for us. So with that, let's get started. So the current threat landscape is everywhere. From social engineering to cryptojacking to mobile malware, not only buzzwords, but serious threats that have been growing exponentially over the last decade. And by bringing in something like computational storage, it's a new element that's complicated even more so with this growing set of threats that we also need to consider. So what is causing all these threats? Let's set some groundwork here first. So the threat actors that we see, it's just not your ransomware threat person. It's cyber terrorists, it's government-sponsored actors, it's hacktivists, insiders, script kiddies, all sorts of different flavors of organizations and individuals that want to get into our systems. And these motivations behind these actors can be political, they can be for financial gain, they can be notoriety, they could be revenge, all sorts of different motives. So really, we need to step back and think security is really a people problem, isn't it? And as we get into how are we addressing these spaces, so this multi-layered Venn diagram that you see in front, the gray oval, really focuses on the moral principles that govern a person's behavior, on why they would conduct such an activity. So there's some root cause psychology that needs to be performed here. The next, let's look at the two larger circles. So on the left, the yellowish circle on privacy. Privacy is a huge concern for across data quality, around data that is purpose-driven. Think of medical records. It's really only for those that have a need to know. Limitations, how do you put in the security guards around, safeguards around that data limitations? And how do you have that accountability around both individual and privacy requirements? And now if we look to the right-hand side at the green circle, now we're dealing with information security itself. The CIA, it's called, of confidentiality, integrity, and availability of information. How is that protected? And then we get into the smaller circles, the cybersecurity one, which is the orange colored circle on confidentiality, integrity, availability of data, how to protect and detect and respond and recover. This is really how to be hands-on with protecting the secure data that is necessary. And then the last circle, the blue circle, is about personal data protection across supporting the various laws and regs that are required by the financial organizations, the healthcare organizations, and so forth. So all of these, of course, have overlap. And so it's a multivariable, very complex problem that we as a systems and solutions community need to respond to, and also, as best we can, come up for opportunities before they occur, where threats and actual breaches actually occur. We need to think through them so that we develop mechanisms within our documents, our standards documents, and within our systems to defend before an actual attack has an opportunity. So that's a lot to be said there. So let's take it to the next level. And just, I suppose this is the final summary slide before we get into the nuts and bolts of this presentation, where we're talking about data security is now at least on equal footing as information assurance. Data protection is the brother or sister of data security as well. So to sustain information assurance, it used to be 5 nines, 6 nines reliability, still is, but now we have to add on this additional layer of information security, which has always been there, but now as we're deploying an exponential growth in applications from cloud to edge, there's more to address, both from the confidentiality, integrity, availability, accountability side for data security, and on data protection, the reliability, the availability, the fault management and prevention on the data protection side. So in essence, what we're saying here is that there is information assurance and then also the ability to recover from failures and faults as well as security attacks. Now, what's happened is that as these attacks, we talked about how they've been growing exponentially. If you look on the left-hand chart here, it shows the timeline of various notable attacks from Google Aurora incident back in 2010 to the Intel meltdown that happened early in the 2010s to the latest, which was a ice-like security bug which was uncovered. And so standards and regulations have been reacting to develop safeguards based on these type of black swan or landmark events, from the FIPS committees to NIST and other various regulatory requirements and security standards that have been developed. Now, as we get into the right side, this really is a nice chart to start to educate us on all the additional insertion points that a bad actor now has at his or her disposal. All the way from, if you look at the edge to cloud, you have customer and IoT, which basically our smartphones act as IoT devices, through data in flight going across firewalls, routers, switches, to within either an aggregation point before we ship data up to the main cloud data center. So basically different phases and train stops for the data to hit that need to be fully protected and secure. But there are these opportunities for root of trust to secure the hardware. We'll get into a little bit of that in a moment. But the key takeaway here is that you can see all these insertion points as a illustration, and I'm sure you could think of additional ones as well. The other point here, we talked about the data in flight and how to consider network security, both challenges and solutions there, but think about data at rest specific to computational storage. Now we need to have robust keys to address ransomware attacks. We need to have solid state drive media and key encryption within those solid state drives. And then on hardware root of trust, dedicated security engines to ensure secure boot, secure firmware, and key management across all the peripherals. So now let's get into computational storage, which is going to drive this point home further. So I'll go into just what is a computational storage drive as a refresher. We'll talk about some of the additional risks that may be exposed by CSDs, computational storage drives, what we're doing as a community to provide better security, how to address risks around specifically computational storage, and the call to action for all of us. So here is on the left is a computational storage drive overview, and basically the context is instead of the standardized means of you have a host CPU or a cluster of host CPUs that are moving data back and forth across storage. And of course that's been an issue because of latency and bottlenecking and so forth. What we're doing now is we're taking, it's called in-situ processing, and move that directly localized to the drives themselves. So what does that do? Well, it does two things. One is you can minimize the amount of traffic going between the host and the computational, or between the storage. And that basically frees up those networking pipelines, highways, to move far more efficiently than they could when they were bottlenecked up with too much traffic, and basically the data had to wait its turn to have access to the host. So what we're doing now is we're pushing down specific data loads and functional calls to the drives themselves so that they can compute on the localized data within the drive. That does two things. Number one, it frees up the traffic bandwidth on the network. And number two, it actually provides more efficient computing because you don't have to go back and forth between the host and the computational storage drive. You can actually do your computational tasks localized, come up with some results, which could actually impact a local decision point that needs to be made. If it's, say, a threat of an intruder that's been detected in a video context where the data was collected in a computational storage drive, say in a smart city application, you're able to take care of that situation locally versus having to ship off all that data, localized data, up to a host, which could be not co-located, but at a remote location. So you see the benefits there. Some of the deployment examples on the right would be basically having an offload array of engines that can support the host, so the host can continue to do and manage control functionality and processing, but offload some specific functionality to the drives, computational storage drives. The other is a smart cache layer where you're able to apply faster media through flash and potentially persistent memory within these computational storage drives, do some localized compute, and basically augment a compute storage solution where before you would be directly accessing the data stored in the hard disk drives. Now you're able to perform some localized computing and providing a higher performance system level aptitude. And then in cloud to edge, as I mentioned earlier, here's the idea that you can send some of the data up to the cloud, but maybe for some of the shorter term decisions that need to be made on the localized data, you can use one computational storage drive or an array of drives to perform those tasks. So hopefully that gives you a nice overview of the benefits of computational storage. And if we get under the hood of a proposed computational storage drive architecture here, or a potential one, you can see that there is a solid state controller, which is managing the NAND media with some peer-to-peer communication between perhaps a number of solid-state drives and accelerators, either within a bank of computational storage drives or all in one. And these accelerators can be FPGAs, ASICs. In this case, we're suggesting it's an FPGA, which can be programmed to offload specific functionality from the host and perform those applications right there, versus having to send the data up to the host. And so now we're looking at two specific functions within the PCI Express address space to consider: the NVMe solid-state drive interfacing, as well as the accelerator itself, the FPGA, which is now providing the computation support for that drive. So if we go back to the threats of security and we look at how a solid-state drive on the bottom rectangle here, it has a number of things to consider. So both you have all these functional blocks within the solid-state drive, which need to be supported within, in this case, a root of trust. So one secure block that contains the MACs, the encryption blocks, the different keys. All these can be contained within a root of trust block. And then the NAND drive, the self-encrypted drive, can also provide further security. So basically you have that solid-state drive function secure and defended upon attacks. But as we mentioned earlier, you have in-flight data coming into the solid-state drives, both in-band and out-of-band. So those also have to be addressed through various encryption mechanisms to ensure that the data is secure both in flight and while it is at rest in the solid-state drive. So this is a really nice chart that I'll walk you through on basically the threats around the different levels of computational storage within these drives. So on the left, connected, so you've got 1, 2, 3, 5 blocks connected to the bus. On the left, you've got a traditional storage drive, which has a storage controller and some storage media connected to a bus, which then in part connects to either a host or an array of hosts. Okay. So the next block over is a computational storage processor, where now you're adding just that, the computational storage engine in green. And the point of this next block is you're adding another level of complexity, which provides an opportunity for an attacker to come in and challenge the security of a more complicated system than just a standard drive. If we move to the right, the next block over, now we're getting into not only the computational storage processor, but the computational storage drive itself, which combines the left two blocks. So both the storage drives and then also the computational storage element. And then if we move to the next one over, 4 blocks over, we can see that now we're looking at providing both the computational storage engine as well as the storage controller itself, providing transparent storage access as an option. So different, and proxied storage. So now we're even adding another layer of complexity. And then finally, as we move to the right, here we're suggesting an array of computational storage drives. Perhaps they're connected to each other and peer-to-peer. So that just as we built up the cake of complexity here, there's different factors to consider. So versus standard storage, a CSD can delete, it can add, it can modify data on the drive. And the drive can also be programmed. It can be run, it can be supporting as a virtual machine as well. And then also risk versus external accelerators. So you have now direct access to storage, you have FPGA programming to deal with, and then access to networking infrastructure, NVMe over F. Decryption of the data prior to processing is also an exposure point for the data, either in flight that arrives at the drive or data at rest. So different security functions that need to be considered are authentication, host agent to the computational storage drive, authorization, which is securing the data access and permissions across those drives, encryption on the data, and then auditing, able to generate and retrieve secure logs. So if we go to the next level of detail, so we mentioned the FPGA as the de facto accelerator here. FPGAs can be keyed and then loaded with encrypted bit streams. Typically AES 256 is used, and these bit streams hold the specific design that will be run within that FPGA upon boot up. So over the last few years, companies that focus on FPGA development have also built out regions of isolation for further defense with actual fencing around those regions. And this allows design region isolation. It allows the programmer for just-in-time partial reconfiguration, which is a fancy word of just reprogramming the FPGA or parts of the design logic that runs in the FPGA so that the full design is not exposed. Also, the system on chip or the compute element can be isolated from the design itself, and programmable user files for device dependency can also be deployed where only those approved users of the FPGA, per se a policy that's been deployed, have access to the FPGA. And then there's e-fusing, which has been available, where basically if there is a breach, then the FPGA can blow a fuse and shut down. So there is that level of device security now that's available. And this link below goes into far more detail, really good overview on this type of FPGA security and programming. So now if we jump over to what are the standards organizations doing around storage, computational storage security, I'll highlight two here. So SNIA has a computational storage technical working group, which does address within the computational storage master document host access and interface challenges and solutions, considerations in defining better security. API standardization is also in progress with keeping security in mind. This specific document I'm referring to is expected for preliminary release at the end of this year. And then there's the NVMe Computational Storage Task Group, which also addresses device access, interfaces, and implementation concerns. And its respective document is expected out the first quarter of next year. So make sure you take a look at that, both of those docs. The other key part here is when we look at cloud service providers, the hyperscalers in particular, each one really does have its own mechanisms for maintaining security policies, both for data in flight, processing requirements and data handling, buffering and caching of data, data at rest policies, how they manage containerization, virtualization, multi-tenancy. And then furthermore, all the major hyperscalers now have edge initiatives and are ensuring that their ecosystem partners are supporting these policies as the data moves back into the cloud from edge to cloud. So very important to work closely with our hyperscaler community members as we address this challenge, but also come up with solutions that support their policies. If we get into some of the security concerns more in an organized manner, I'll take you around this wheel. So there's root of trust, Microsoft Cerberus, and OpenTitan by Google are two examples. So is Intel TXT and TPM. Cryptography, FIPS 140-2 is the known standard to mention here. Secure enclaves, NIST, OCP, and are also two good example initiatives that are supporting secure enclave. Self-encrypting drives. Number 5, key management, such as from TCG DICE, NIST, and DMTF are also providing and promoting standardization on best practices for key management. And then security lifecycle, which is the 6th category here, manufacturing vendor specific support that needs to be considered. NIST and SP800 is a great standard to look at there. And so if we go through just a quick overview on each one of these. So OCP, Cerberus, root of trust, the whole premise here is to enable secure boot across all the devices, whether it's an FPGA, a processor, a NIC, to prevent physical and side channel attacks. And then also provide automated and secure key management. So this illustration here shows a Microsoft storage server with 40 Cerberus approved chips to support a root of trust subsystem. And then on the right, you can see various components similar to that diagram that we showed earlier, where you have both encryption and then puff files and secure key management all within this root of trust block. So that gives you just a quick snapshot of the root of trust. If we go into crypto, basically here it has to do with security strength. If you go to the bottom table, you can see that there's AES has migrated from 128 to 256. ECDSA is now migrated to 384, and RSA has a more secure standard from 3072 to 4096. And NIST and FIPS 140 are the critical standards to look at here for cryptography. And then for secure enclaves, number 3, basically this is a way of defending against side channel attacks through power monitoring, EMT, and timing. And the secure enclaves are also recommended by NIST and provide a common criteria compliance that's required by the cloud companies to provide a secure enclave. Number 4, this is self-encrypted drive technology. This suggests that the left side, you can see that you're moving from a bank of secure encrypted drives, where here there is no specific host software control, whereas then you're moving into software-driven volume encryption over a bank of drives. And then to the right, both hardware volume encryption along with an external key manager, and then KPIO enablement as well, just to add a further level of security. And then number 5, key management, focuses on protecting keys from threats and ensuring security of keys through the life cycle of the solid state drive, all the way from deployment, manufacturing deployment, to production deployment, and then to end of life. And then lastly, the security lifecycle here, where you're able to expand upon that, and from design all the way through retirement or end of life, you're able to have a secure implementation and protection from manufacturing phase to vendor ID injection to when you're actually going to decommission and retire the drives themselves. So those are the 6 main categories of security that we need to consider. This is just a nice summary table on the security pillars that we walk through on root of trust, crypto, secure enclaves, self-encrypted drives, key management, security lifecycle, and some of the schedules that are being supported by Cerberus and OpenTitan. And this is my final slide. So basically, computational storage provides a better application performance. It removes the bottlenecks. It provides additional compute power. It provides localized compute power. But now we have new security challenges to solve, both for data at rest applications, for process data, for computational storage to host data. Cloud service providers already have their own data security policies that need to be supported, and hybrid cloud deployments need to address security concerns both for on-premise, co-located, or edge-to-cloud deployments. SNIA and NVMe, those are the principal working groups that are working on computational storage architectures with security in mind. And so my suggestion to all of us on this call are to continue to participate in standards committees and contribute to secure computational storage ecosystems by providing use cases and specific applications that our customers are seeing. And that's my presentation, and thank you for your attention.
Thanks, David. That was great. A great presentation. We do have one question about the standard way to secure streams of data, but let's carry that over to the Q&A that's starting in a different window right now for computational storage. And I think you're on that one, David, as well.
Okay.
To answer that one, let's go ahead and move over so we can keep on time, unless you can answer it in like a minute.